Okay, cool. All right, well, thanks everybody. Actually, what we were talking about earlier is really great because it segues into what I'm going to talk about here. So I just want to take a few minutes to introduce our program and then actually talk about trying to get more interaction between our group and things that we're doing in our department. Okay. So just a little introduction about where I work. I'm full-time faculty, applied math. I teach in the computational finance and risk management program, for those who don't know. I actually spent close to 30 years in the private sector, and now I'm teaching full-time. So I'm a bit different from the others there in that I'm not a tenure track professor, just that's what you call a teaching professor, but I love every minute of it. I really enjoy it. But having said that, there's a picture of our building, and you might be happy to know if you come by, it was retrofitted over last summer, so now if we have an earthquake, it won't fall down. So that was cool. They kicked us out over the summer, but now we don't have to worry about it. Okay, so just a little disclaimer. I'm giving this presentation on my own, just for personal introduction, kind of friendly thing, so I have not been sent or dispatched officially by my department, so just in case. All right, so anyway, a little bit about our program. Up until now, we've only been a graduate program, although we have some courses at the undergraduate level in a joint program with the Department of Math, and I think computer science falls in that as well. But our graduate programs, we have master's degrees in applied math itself, and then also the program that I teach in, which is computational finance and risk management. We also have a PhD program, and it is, I don't want to sound arrogant, but it is one of the top programs in the country. So it's actually quite an honor to be part of the department there. Starting next academic year, though, we are going to have 2 undergraduate programs. This is hot off the press, just was approved and final approval, and so we'll have a Bachelor of Science in Applied Math and in Computational Finance. So if you're interested, here's some URLs. I'll post. We'll have this posted on the website when this is over. Jeez.
And I mentioned we're going to be in another room next month.
Yeah, that's nice. Yeah, had I known, I would have brought my rig in and cranked up some porcupine tree. Anyway, okay. So the research areas, okay, near and dear to our hearts here is scientific computing. So there's a lot of this that is going on in the department, and then modern mathematical methods is kind of general, but there is that. Some of the application areas, we are applied math, so what are some of the application areas? Mathematical biology, computational neuroscience is quite big. Nonlinear waves involving PDEs and numerical solutions of PDEs, partial differential equations. So again, this is where a lot of heavy computation is necessary. Mathematical finance, which is what I'm involved in. But we do have PhD students who do their dissertations in this area. Medical imaging is another one, and climate modeling. So there is a strong emphasis on scientific computing, although most people there tend to use Python and R. Julia is also somewhat big, and we do, at least one professor has a strong tie with the people at Julia at MIT. But there is also C++. It's not used quite as much. I've actually been involved in a few things where an R package was developed, but it needed to be sped up. So we moved that part into C++ and then interfaced R with C++. So you have the convenience of R. You can call the functions like you would just any other R program. but what you're actually doing is you're calling functions in a library in C++. So as far as C++ goes, again, if you talk with most people there, most of them will probably be using interpreted languages. But what happens, of course, is that they reach their limit very quickly. And so what researchers have to do is port their programs onto massive distributed systems, which can be kind of a pain in the butt. But this brings about an opportunity for C++. In fact, I'm now talking where they get some talking with one PhD student who actually has this problem. So she has to put everything out on a distributed system using Python. So we are now talking about possibly moving some of this to C++, see what we can do. So as I say, it is used and it is taught in our programs, but it's not used nearly as much as our Python. And there's some Julia. There's one group that was doing a lot of work, I think it was in medical imaging, and they're doing a lot of their work in Julia, but what was happening was they were working with other universities, and they were all R people and Python, so they had to kind of bag Julia in order to, please the rest of the community working on that project. But post C++ 11, as we know, it's far easier to implement mathematical models, and as we go towards C++ 20, it's getting better and better. But unfortunately, it's I like to imitate Rodney Dangerfield, but it's still not getting the respect it deserves, in my opinion. And there's still this there's this perception that C++ is too hard. You're always going to have problems with memory leaks and the whole litany of gripes. But it's just not that way. And I think this is an opportunity for us as perhaps as C++ programmers to maybe show those who are active in real cutting-edge research that there is an alternative. It's not that hard, and you don't have to. You might even be able to do all your work on just a single node rather than these massive distributed systems. I don't know yet, but that's what I want to find out. That's a hypothesis I want to test. Okay. So the other thing is I mentioned earlier, and we've done some of this, I've worked with a few people on this already, is to delegate the heavy number crunching to C++ and then interface with our Python. Done this with a few financial packages, actually, and advanced statistical packages in R. So I mentioned the ongoing and future work, I hope, with researchers and PhD students there. So this, again, I'm trying to cultivate this. So it's developing. Maybe 6 months from now, I'll have a little bit more information. But it's like my gut. I'm working on it. All right. As far as quant finance goes, I've also been working on building up opportunities for our students in our CFRM program. In fact, we have we actually have two students here from the program, but one in particular, Stephen Jung, who's sitting in the back, who last quarter put together a really nice, a set of examples showing how to use PyBind 11 and to take some of the pain out of the process of interfacing Python with C++. And so it's on, I've cloned it to my GitHub site, which is here. And if you're interested, it would really be great if you try it out. be interested to hear from you. I've also been involved with some cutting-edge statistical distribution research for financial modeling. What this is more advanced four-parameter distributions, which will capture the fat tails better, which you find in financial returns, and the skewness. So a couple of Google Summer Code projects in particular. But what we did was we took the stuff that was just too slow in R, we moved it to C++, and then we wrapped that C++ library inside an R package, which then accompanied the project. Some other things, random number generation conformant with C++ 11, and PDF, CDF, and quantile functions, which have been written as if in the same way that they're presented in Boost. So again, this is one of these advanced four-parameter distributions. We're trying to tie this up, and I hope to push it out soon. Also, dates and day counts are extremely important in finance. It's, I know, an incredibly boring topic, but if you get them wrong, then your competitors can arbitrage the hell out of you and make millions while you lose millions. So it's very important. With C++ 20, we finally have a proper date class. Yeah, it's about time, right? C++ finally has a date class. Took them 30 years, but we got one. So what we did is use that date class at the core of what we're doing, and then wrapped our stuff around it. So it's more applicable for use in quantitative finance models. And then I've been on and off working on a scenario generation library. This is something that's used in risk management, and the math can actually get kind of heavy, but it's kind of fun. But with some of the newer features in C++ 11, so concurrency and parallelism, task-based concurrency, great. The random features in C++ 11, also great. And so we can use these and put together this, what I'm hoping is a scenario generation library, which takes into account equities, interest rates, foreign exchange, and volatility, and then you also have the correlations between some of these things. So it can get kind of hairy, but it's very interesting math. And not only that, now we have better tools in C++ compared to, say, 15 years ago when I was actually working in the private sector. We had to write a lot of this stuff manually, but now it's available to us in the standard. The standard's getting even better. Add to that the parallel STL algorithms in C++ 17, and I mean, we're really starting to rock. But again, we need to get the word out. I don't think there's the C++ community has done that good of a job of really pushing these features. And by the same token, people in research don't know about it because nobody tells them. So, to wrap it up, what I would really like to have is to develop more support and input from you all. And in particular, try out our stuff, kick it in the tires, give us some criticism. Don't flame my students, you can flame me, okay? But we'd love to have you try this out. And starting with the PyBind 11 material that we have so far. I mean, I've heard from a number of people here that how painful this can be. So we'd love to have you try it out, let us know. Mentoring opportunities. If you have a little spare time, and suppose we have I do work with students individually on C++ projects, but there are times where we hit a brick wall with some advanced topic in C++. It'd be great to have some of you help us out. And that ties in with, just ad hoc help. Something comes up. It's like, oh, dang, what do we do here? Maybe a few of you might be available just to, I'm not saying we need 24/7 support, but I know like a mailing list or something. Say, hey, we're trying this out. Has anybody tried this? Or say, C++ 20. Have you tried this new feature yet? We're trying to use it here. So these would be really, really great if we could get more interaction between some of the stuff we're doing in our department, and in particular, the work that I'm doing with my students and with some of you here. That would be really, really great. Okay. So that's it. Thank you very much. And just a little picture here at the end. I can't get by without injecting a little humor. So, all right. So thank you very much, and I'll hand it over to our VIPs from DigiPen.
Okay. All right, hello everybody. My name is Michael Paul Moore. I work at Monolith Productions as an associate software engineer, and I'm a DigiPen senior currently. Today I'll be sharing with you a concept I refer to as type runtime. So before we go into what type runtime is, I'd like to talk to you about what I was trying to solve when I decided to build this. So the different problems are authoring classes at runtime. So in a student project, I wanted to get away from having engineers build all the classes and data needed to derive gameplay and other things, and start having designers build that stuff. But with that came then the problem of, well, we wanted different features to be usable, like being able to convert an object into a string, deserialization, comparison operators, being able to show it up in the UI, features like that. And with that, we also didn't want these features to be so coupled with the classes themselves. In my second year project, we ran into a lot of an issue where we would create a class and we would create a feature for it, but that required the engineer who generated the class to both understand their class and the feature, and then every time a new feature came out, that engineer would have to be trained in what that new library or tool we were integrating into it, and it slowed down production. And at the end of the day, most engineers, they just didn't implement it because they were like, I don't care, I want to make code. So to do this, I made this idea called type runtime. And type runtime is built off of two concepts. It's just really basically focusing on like how C++ even builds classes and stuff like that, and recreating that in a more flexible way. So we have the type structure and the type data. Structure is, that's actually incorrect. It defines the class. It has more verbose information. So this is like equivalent to your class declaration. When you say class name, it's equivalent to that information. And the type data is just simply the data associated with your class. So focusing on the type structure, it follows the one definition rule where you have one per type you have. So if you have a transform, you just define a transform. You can't have two, unless you make a new class. It contains the variable names, the types of those variables, and locations of members in memory. And with that information, it can translate that into knowing where in memory, that it translates into like indexes and such, and the size of the class itself, which is useful later on when we go into the type data. So the idea of this too is separating that because it lowers the complexity of your class that's being passed around the data itself. So I'm about to show some code, so this is a little slide to show what everything means. So see, TD is type data, TS is type structure, and TP is type proxy, which I won't be talking too much about that. And then I'm using STD. So here's kind of an example of me doing this with a simple transform in like a 2D environment. First I define my base type. So in this case, my base types I need is float, and I define the size of the float. And then I define my actual types, which I have a vector2 and a transform. And vector2, I could be like, it's a float x and a float y. And then transform, because vector2 has already been defined, just needs to know that the type vector2 is being used, and the name of the two we're doing, in this case, position and rotation. Yes. So with that, now we need kind of a process to be able to convert our type into, convert our classes into runtime types. And as you see, it becomes very boilerplate. I am going to gloss over kind of like how I have this comment here. You can iterate via index members. I'm not going to show how that's being done, but it's basically it's utilizing that structure you've built. You pass your, if you see this line, the second line, how I'm saying like, hey, type data with vector2, so that gets passed internally. It checks what's the size of vector2, it allocates the necessary memory, and then when you index into it, it uses the type structures information to know, oh, at index 0, it's this point of memory, index 2 is this point of memory. It's literally just doing simple math to calculate, like, all right, that's 0 for index 1 and 4 for index 2, because it's the size of a float. And then for transform, it operates on the same process of knowing the name of position. Okay, this is the type we're looking for, meaning the member we're looking for, position, where is that in memory, and it's returning that piece of information for us. And then this is going from our runtime types 2 classes. You can see that the code is nearly identical. It's a little maybe simpler in this case. But yeah. So back to kind of like one of our end goals. So the idea is to be able for me to do something like, I have this type data, there's a vector2, and it has these values, and then later down the line you want to like print it. And you may not want to just print vector2, you may want to print a transform, or you want to print whatever, but you don't want to make that functionality per class, because you just want it to be like, you should just know what my class is, I don't need to implement it. And that's kind of what the output may look like. So this is kind of a big block of code to show like this works, this is the code that does that. And this is really interesting because I've made this very generic algorithm to handle iterating through your classes recursively, and I know that this code will work for any new type that I throw at it. And so getting towards the end, so here's some tips that I learned along the way that kind of help make things easy. I have a proxy class for type data, so I like to view type data as the actual copy of the class, and the proxy more like a reference. That ended up being a decision made because it was easier to manage memory, because you end up doing a lot of like slick things with iteration and moving things around, and if you don't have like a proxy class handling it, you end up having to deal with a lot of like constructors being called when you don't want to, or like having to manage memory in more complicated ways than are necessary. And then next most important thing probably with all of this is this little helper class, which we'll go into in the next slide, which is kind of the double green arrow I have here. This is kind of like that's handling the base for the base classes, and that's where like the magic happens, per se. So how that's being handled is I just have a simple interface class that has these pure virtual functions of the functionality I want. So in this case, I have a toString and something that converts by type structure into a, I was using rapid.json for the actual implementation of this. So with that, then all it is a templated class that just calls the function, so it does the templation. So it will call the correct version of toString of my type data. So if my type data is a float, it gets called correctly, because if you look at the second to last thing I have here, I'm adding into a map basically these instances of type helper. So it's a string, which I have that information, some sort of identifier that it is a float, and I know that when I try to call that function already internally does the casting for me, and that speeds up development a lot for creating these very basic types. And then you can see now this works, being able to be like, what's the type of this, and just call the toString function. Moving forward, I would actually like to abstract this a little further. I feel like it's this is separate kind of from the rest of the library. And one complaint I had from somebody who was trying to work with this is they felt that even this was maybe part of too much understanding of the system, and they kind of wanted something more abstract to be like, hey, this functionality, just throw it to it, and I kind of catch it and be able to figure it out. That's the talk. Any questions?
So are you using type traits in that?
No, I'm not actually.
That may help you with having to do that time.
Well, so the big thing is so when I think I first started doing this, I started using some of the C++ type runtime stuff. The issue is that I started breaking the rule of I wanted people to be able to author classes. So like if I was to use some C++ implementation to specify, like say a transform, the problem is so let's say I actually wanted a designer to have built that before I started implementing it. That's where then I start having to make something that kind of glues that together, and it becomes kind of messy. Any other questions? Yeah.
Okay.
So I'm Lux Cardell. I'm a senior student at DigiPen in the Bachelor of Science in Computer Science program. Last year, I was working on a full 3D custom engine implemented in C++ with the intent to support designers. We were hoping to use Lua as our scripting language because it's lightweight and easily embeddable. So instead of writing binding libraries for every single function we wanted to bind in our engine, I decided to do the lazy thing and write a template for it. So basics of Lua, it's a loosely typed scripting language like Python. It's designed to be fast and lightweight, and it compounds, instead of classes and structs, it makes compounds objects using hash tables. So everything's just a lookup in a table if it's not pure data. So, and additionally, object orientation can be implemented through metatables, which are basically just a table that holds functions, sort of like a vtable pointer. So the C interface uses, afterwards, I'll get to you.
Afterwards?
Yeah. So the C interface uses a standard function signature for binding functions. They take a Lua state pointer, which is essentially the Lua environment, and they return an int for the number of values returned from the function. My current implementation here doesn't handle returning multiple types or multiple data values. So for the most part, I haven't really touched on that. So in Lua, the top 3 lines show calling a function, add, which adds 2 numbers and returns the result. This is a basic binding function for it. It's doing no validation or checking for the actual data to make sure that it's correct. It just calls the function and pushes the result. So this is the declaration for my actual binding function. I had to wrap it in a struct because I needed to use the return and the argument package from the external template. These are the helper functions I'm using. Check single arg checks a single arg, pretty standard, off the top of the Lua argument stack. Check args goes through the entire argument stack and checks every single one for the argument values or argument types that we've given it. Pop args pulls all the arguments off of the Lua stack and puts them in a tuple. And push result is the function we use to return a value to Lua. So this is a generic type structure that I've created just to make interfacing with the Lua stack a little bit easier. I've only supported 4 of Lua's actual data types for this because it's a little bit more complicated to go into pointers and tables. So the big big part of this class is the constructor and the get value. I don't know why it's formatting some of that weirdly. Anyways. So in order to actually bind a function, there are a couple things that need to be done. We need to check the validity of our arguments. For instance, the number of arguments and which types the arguments are. And we need to get the arguments off the Lua stack. And we need to call the function with those arguments that we popped off the Lua stack and then return the value onto the Lua stack. This is the introduction or first part of the binder. This is the type checking. So it first checks, it uses Lua get top to get the actual size of the stack. Checks that that is the size that we're expecting. And then if there are arguments that we want to pass in, checks that all the arguments are valid. Next, if there are no arguments, we can just call the function, which is pretty easy. We can just call it. If it's returning something, we will need to push that return value. Otherwise, we'll have to get the arguments off of the Lua stack and then go through more or less the same process. I'm using standard apply to pass a tuple of arguments directly to a function. Checking the types has to be done through manual implementation of each type that you want to support. For instance, integers and floating point values could be done like this. They're pretty simple functions, which is a lot easier than writing an entire library of binding functions. So in order to actually check the argument types, I have to unpack the parameter pack that I passed in the struct template. So I check if the argument is, I use the check single arg function to check if the argument is valid. And then if there are more arguments to check, if there are no more arguments to check, I return true. Otherwise, I call again with the rest of the parameter pack. This one is another recursive function. I used the Lua value structure earlier here to just create, or to automatically pop the value off the Lua stack. And then at the end, I, similarly to the previous one, call it again. These are instantiations of the push result for integer and floating point values. So there are some limitations to this. Primarily, it only works when you've explicitly supported data types. It's also not very reference friendly because templates don't play very well if you haven't instantiated something specifically for it. It also doesn't account for nil values, which Lua likes to use as a this argument doesn't exist. It's possible that we could implement something that would take the default values and apply them in the place of nil values, but currently it just errors out instead of doing anything. I haven't supported Lua's user data type here, primarily because it takes a little bit more in-depth templatization, and I haven't supported multiple return values or returning arrays of values because it would require converting a tuple back into arguments and pushing them onto the Lua stack individually. So all the code is available on my GitHub, and you can find me on LinkedIn. Are there any questions? Yes?
On your very first slide, you gave a brief description of what Lua is.
Mm-hmm.
And I don't know much of anything about Lua, but I do know JavaScript, and that sounds like a description of JavaScript.
It's very similar to JavaScript. The main difference between Lua and JavaScript is that JavaScript actually has things that are implemented for it, and Lua has more or less nothing. It's as bare bones as you can possibly get it, which is part of the appeal of it because it's very lightweight and easy to embed and you don't need extra functionality.
Well, I'm curious how it could be fast when your field lookups are all hash tables, because I know that's a problem with JavaScript.
Part of what makes it fast is not the way it's implemented, but rather the way you can use it. It's very easy to bind, which means that doing things with a C++ or a C backend is much easier and much faster than writing everything in the scripting language.
It has a jig compiler that does everything. So the hash will go away. Okay. Well, I have one question. Do you plan to implement those other functionalities to make this a true
So
usable library?
on my GitHub, it is implemented with user data supported. I just didn't go into it in the talk because it was a little bit more complicated to do.
So how much back-end processing do you need in C++ that Lua cannot do for you? What's the advantage?
The advantage of using Lua is that it's much less in-depth than C++, which makes it a lot better for designers to use, especially people who are not programmers at all and would rather stay away from programming as much as possible. All right.
Workloads using C++ 17 parallel algorithms for rapid prototyping. And so an overview project, I have an engine that I've been working on, and it's single-threaded, so I figured I'd try to make it multi-threaded. And so since there's demand for that sort of experience, as well as the fact that performance-wise, it tends to scale pretty well on the right hardware. So what I had was an OpenGL renderer that's inherently single-threaded because of OpenGL, and a physics engine that's also single-threaded. And so to achieve the goal, I ported the OpenGL renderer to Vulkan, since that has support for parallel submit of draw commands, and I parallelized the physics engine as well. So this second part is the focus of the talk. And so the parallel algorithms feature added new algorithms that parallelize well, as well as the execution policies for these algorithms, and 20 adds the new non-parallel and sequence policy. And so I'll be focusing on state transform reduce using the parallel unsequence policy. So state transform takes multiple inputs, does a unary op, and produces multiple outputs, one per input, and state reduce takes multiple inputs, does a binary op on all available pairs until there's none left and you have a single output. And combining these two, you get transform reduce, which takes multiple inputs, transforms them, takes the results, reduces them to produce a single output. And this was basically the Swiss Army knife for the entire parallelization strategy. And it's basically the map reduce model popularized by Google a while back. And in a single frame of the physics engine, we have the broad phase, which uses a bounding volume hierarchy to do early rejection tests based on the bounding volumes. The narrow phase, which takes the overlapping bounding volumes and does the actual collision test. The force integration step, which updates the velocities. The constraint solve, which resolves the constraints, such as for collision resolution. And then finally the velocity integration, which produces final position update. So based on the sort of code flow, the portions that were made to run in parallel were the narrow phase and the constraint solver, since for the rest they have pretty short runtime for each operation, so it ends up being quite a bit of synchronization overhead, or in the case of the broad phase, it's a binary tree, and making that parallel is not particularly appealing. So for the narrow phase, we have a scene containing multiple objects, and from the broad phase, the bounding volumes that are overlapping, in the current frame. And so we take each pair of objects and transform them into a state list of either 0 or 1 elements based on whether or not they're actually colliding, and then we merge all this lists into a single list containing all the collision pairs. And for the constraint solver, it's a bit more involved, and so we start with a simple case, and we mark them so that we can tell them apart. Yeah. So the solver is an iterative solver that optimizes the corrective impulses, and this is done using a sparse linear system where each constraint is a single row in the matrix, and each subsequent constraint may have dependencies on previous rows. And so for a more complicated system, the approach used was to use an edge coloring algorithm, which produces the colors where no two constraints of the same color end up having dependencies on each other. And so from this, we can rearrange the rows and group them such that they can all be run in parallel. And this is done multiple times until either equilibrium is reached or the iteration limit is exceeded. And so before going into the actual code, let's look at the prototype for one of the overloads of transform reduce. We have the execution policy, which defaults to the sequential non-parallel policy if omitted, and then we have the input range, the initial value for the reduce op, the binary reduce op, and the unary transform op. So this is a simplified version of the narrow phase code. We're working with a list of pairs of object handles, and so we want to transform reduce with parallel and sequence policy over all the broad phase outputs, and the transform op does the collision test, produces a list containing either 0 or 1 elements as previously mentioned, and then it reduces them by merging the list using the splice method of the list to have an efficient merge operation without additional allocation overhead. And this gives you the list of all the colliding pairs. As for the constraint solver, we have an outer loop that does multiple nested transform reduce calls over all the constraint groups, with the inner call running over each group and solving all the constraints in a group in parallel. And the reduce op is a helper lambda that resolves the overload for state max, and the output of the entire call is the largest corrective impulse, and so that allows us to break out the loop early if A falls below the certain threshold. And so in conclusion, using the parallel algorithms gives you less to implement in terms of system level details, and so it's good for prototyping parallelization strategies as a result, and depending on whether or not the target platform supports it, in library support it can be portable, but however there's the abstraction overhead, and so you may need to tune it later with your own scheduler implementation for better task distribution.
Did you actually do performance analysis to see whether just doing it straight?
Yeah, so the collision detection was basically, it was a huge speed up because pretty much every collision test was done in parallel, though the cert list was a bit of an issue since at the end of the function you have to deallocate the whole thing and that was linear time. But in general, given a better container, it might be viable. So, but the constraint solver, the issue there was that for more regular cases, it was actually slower. But in cases where the constraint graph is disconnected, it tends to pull ahead.
Is this done on a single core or a multi-core device?
Multi-core. I think it was
So was it a graphics card or was it was it a multi-core type system or graphics card with a
it was just it was running on CPU. Not really, because it doesn't really, well, on the GPU, it doesn't really split into, the workload doesn't split that well, because on the CPU you have like a small number of cores, that's fine, but on the GPU there's too many cores, it doesn't really, the workload doesn't distribute over all of them. But NVIDIA actually had this thing that they're trying to do, but that was what I was originally going with, but it doesn't actually scale well in terms of number of iterations. It doesn't converge faster if you throw more iterations at it, so I went with this instead. Anything else?